Hi everyone, today we're going to continue on with 3.1, using and expressing measurements. So yesterday we kind of learned what a measurement was and we went over some scientific notation, but today we're going to go over two other important concepts, and that is accuracy and precision. So in chemistry, the meaning of accuracy and precision are quite different. If you want to know the definitions for the two, they're located below. Accuracy is the measure of how close a measurement comes to the actual or true value. So the key word here is the actual value. If I was trying to measure out 15 milliliters of water and I got 14.9, that's fairly accurate because it's really close to how much I wanted to measure. Precision is a little bit different. Precision is the measure of how close a series of measurements are to one another. So for example, if I was measuring out 15 milliliters of water and I measured out 11, 11.1, 11.2, those are all around the same measurement, so they are precise. Now this is irrespective of the actual value, so even though all those measurements around 11, we're not close to 15, that's okay, we're still precise. We're just not accurate. The other thing I want to point out for precision is also how detailed or how the closest reading you can get on, let's say, a measurement tool. So like a thermometer or a beaker or Erlenmeyer flask. So how do we evaluate accuracy and precision now that we've kind of talked about the two differences? Well, to evaluate accuracy, a measured value must be compared to the correct value. So that means if you're going to measure accuracy, you actually have to have a correct value to measure it to. For example, 15 milliliters was my correct value, and then I take another measurement, and I'm comparing to that 15 milliliters. We have an example coming up with a bullseye if you're throwing darts. Well, the middle bullseye is what you want for your correct value, and your accuracy is how close you're going to get to that bullseye. So again, accuracy needs a correct value. To evaluate precision, you have to compare values with two or more repeated measurements, which means in order to do precision, you have to have multiple measurements. Because in order to even do precision, you have to compare them. And if you don't have anything to compare it to, well, that's not going to work out. So here's a good example that I like to use because it does help explain the difference between the two. Darts on a dartboard illustrate the difference between accuracy and precision. So when you play darts, if you've never played it, the whole goal is to get it dead center on that bullseye. It gives you the most amount of points. So the closeness of the darts to the bullseye corresponds with the degree of accuracy. So if you hit that middle, you're accurate. The closeness of several darts to one another tells me precision. So let's look at this first dartboard. I have good accuracy because I've hit the bullseye, or I'm really close to it. I also have good precision because all of those darts are really, really close together. Over here, I have poor accuracy because I am nowhere near that bullseye. But I still have good precision because, again, all these series of measurements are really close to one another. So although I didn't get the value I wanted, I was consistent. So you can kind of compare consistency to precision. And the last one, I have poor accuracy because I never really hit the middle of the value that I want. And I also have poor precision, or I was very inconsistent, because all of my darts are nowhere near the same location. So here's a question that I ask on all my tests. So yes, this will be a test question. So if you want to start in your notes, it will be. It was also, I believe, a question on your guys' pre and post test. So you will see it on your final test for this class. So are precise measurements always accurate? So I want you to pause this video and kind of think through it and see what you come up with. So if we were to look at this, no. Measurements are precise if they are easily reproducible, but not accurate if they do not reflect the accepted value. So are precise measurements always accurate? No. If we actually go back and we look over here, I have a precise measurement right here with all 3 darts at the 20, but I am not accurate. So again, no, precise measurements are not always accurate. Another example is I can have a clock, and my clock always runs 5 minutes late. So even though it always is precise and consistent and runs 5 minutes late, it's never going to be accurate because it's not running the correct time. The last major concept we're going to learn about is something you'll need in order to do your lab for today, and that's determining error. Error actually allows you to see how accurate and precise that you are. So suppose you're using a thermometer to measure the boiling point of pure water at standard pressure. Our thermometer reads at 99.1 degrees Celsius. So that's what your thermometer reads as. And you probably know that the true or accepted value for boiling point of water is 100. So again, this is your accepted value. This is what you should have got. And then here, this is your experimental value because this is what you read in your experiment. So there's a difference between the accepted value, which is the correct value. So that, again, remember, is 100 degrees. For the measurement based on a reliable reference, so they've done extensive research and known for a fact that it's 100 degrees. And there's a difference between that value and the experimental value. So remember, experimental values are going to be ones that you measure yourself in lab. So your experimental value, we'll see coming up, was that 99.1. And the difference between the experimental and the accepted is known as error. So your biggest error. So error can actually be positive or negative depending on which value is bigger, your accepted or your experimental. So whether your experimental value is greater than or less than your accepted is another way to say that. So for boiling point, your measurement, the error was 99.1. So you would say C minus 100, or you could say C or negative 0.9. So we were negative 0.9 degrees Celsius off, and we were less than that 100. Now, oftentimes, error isn't alone useful. Most of the time, I'll have you guys calculate percent error, which is what you guys are going to be doing on your lab. You'll find percent error in a lot of other labs if you decide to take advanced chem because it allows you to see how well you did something. So often it's useful to calculate the relative error or percent error in addition to the magnitude of error. So our magnitude was negative 0.9. Here we're going to calculate percent, so how far off. So the definition is the percent error of a measurement is the absolute value of the error divided by the accepted value, multiplied by 100. If you know anything about math, absolute value must always be a positive. Must always be positive. That's what the absolute value bar means. So we just got a negative 0.9. So instead of negative 0.9, this has to be a positive 0.9. So let's look at this. We're going to calculate the percent error of the last equation that we had. So the boiling point of pure water is measured to be 99.1 degrees Celsius. Calculate the percent error. So down in the box it says, think about it. Using the absolute value of the error means that the percent error will always be positive. So that's what I was saying. This is an important concept. Percent error will always be positive. If you get a negative, you have somehow made an error. So let's analyze. List our knowns and unknowns. Well, our accepted value is 100. So we're going to know that as our accepted value. Our experimental value is 99.1. And our unknown is our percent error. So that's what we're trying to find. So then we're going to start with the equation that we know for percent error. So percent error equals the absolute value of your error divided by your accepted times 100 to make it a percent. So then what we do is we have to substitute what we know and plug them into the equation. So we know that our experimental value was 99.1 degrees Celsius. And our accepted value was 100. And then again, you plug in the other accepted value below. And then you're going to multiply by 100. So if I take 99.1 minus 100, I get negative 0.9. But since these are absolute value bars, I have to have a positive 0.9. And then you're going to divide by 100. Then you're going to times that by another 100 to get a percent, so you get your 0.9% off. So you are less than 1% off, which is a very, very good measurement. So does this result make sense? So since it was off by about 1 degree Celsius, it makes sense that your answer is about 1% off. Anyways, that's the end of the lesson, and let me know if you have any questions.